Welcome to this explainer. We've got a seriously fascinating topic lined up today. But to kick things off, I want you to just close your eyes for a second. Imagine you're floating in deep space, millions of miles away from literally any planet. It is completely silent. It's completely empty. So, how exactly do you move through it?
Right? It totally messes with our earthbound intuition. Down here, we're so used to pushing off of things. You walk by pushing against the ground. Your car drives because the tires physically grip the road. Even a boat pushes against the water. But out there in the absolute void of space, there are no roads to grip. There is no air for a propeller to grab onto. There is zero ground beneath your feet. So how on Earth, or rather off Earth, does a rocket actually get anywhere?
Well, to get from basic high school physics to literal rocket science, here's our roadmap for today's explainer. We're going to start with moving in a vacuum, then look at the physics of propulsion, tackle the challenge of decreasing mass, decode the Tsiolkovsky Rocket Equation, and finally, bring it all together by budgeting for deep space.
All right, let's jump right into part 1, moving in a vacuum and the physics of pushing back.
So to solve our little dilemma of trying to move without a road or any air, we have to lean on one of the most famous rules of motion ever written, Newton's third law. For every action, there is an equal and opposite reaction. Seriously, this is the entire secret to rocket propulsion. Inside a rocket engine, fuel burns and produces these incredibly hot, high-pressure gases. The rocket then violently expels those gases out the back of its nozzle at insane speeds. That expulsion? That's the action. And the reaction? As those gases are shoved backwards, the rocket is thrust forward.
What's really happening here is governed by a principle called the conservation of momentum. Think about it like a perfectly balanced scale. Before the engine fires, the rocket and all its fuel are just sitting there together. The total momentum of that closed system is exactly zero. But the very millisecond that engine fires and shoots exhaust gas backwards, that gas suddenly carries momentum in one direction. And because the universe demands that total momentum stays conserved, it has to stay balanced at zero. The rocket itself absolutely must gain an equal amount of momentum in the exact opposite direction. This mathematical balancing act is what causes the rocket to accelerate forward, and it's going to keep doing that as long as it's spitting out propellant.
This actually brilliantly highlights the core difference between the vehicles we fly in our atmosphere and the ones we send into space. An aircraft is totally dependent on its environment, right? It physically needs external air to grab onto to generate thrust. Take away the air, and a jet is basically a very expensive paperweight. But a rocket brings its own party. It carries its own fuel and its own oxidizer right on board. It packs absolutely everything it needs. And that is exactly why it works perfectly in a pure vacuum where there's no air at all.
But, as you might guess, bringing absolutely everything with you creates a whole new headache. Let's move to Section 2, the challenge of decreasing mass and the catch of carrying fuel.
Here is the absolute crux of rocket engineering. It's so simple, but so punishing. Fuel itself has mass, and because it has mass, it dramatically and constantly changes how a rocket behaves in flight. Think about it. Every single second a rocket is burning its engine, it's losing fuel. That means its total mass is rapidly dropping. Now, a lighter rocket is way easier to accelerate, so as it burns off fuel, the rocket actually becomes more and more efficient at speeding up. This constantly changing weight makes flying a rocket fundamentally different from, say, driving your car on the highway. But, of course, to get light at the end, you had to start out incredibly heavy at the beginning.
And that right there creates this vicious cycle of diminishing returns. Let's walk through it. Step 1, you decide you want your rocket to go faster, so you add more fuel. Simple enough, right? But step 2, fuel is heavy, so adding it makes your whole rocket heavier. Which leads to step 3, because your rocket is now heavier, you have to add even more fuel just to push that extra fuel you just added. And boom, step 4, you hit a wall of diminishing returns. Engineers figure out real quick that you can't just add a bigger gas tank to solve a spaceflight problem. The physics literally won't let you.
So how do we outsmart that cycle? We use the ultimate cheat sheet. Welcome to Section 3, the Tsiolkovsky Rocket Equation, decoding the math.
Okay, stick with me here. Don't let the math intimidate you. The relationship between how much fuel you burn and the velocity you actually gain is perfectly captured by this equation. Let's just decode the variables. It's actually pretty elegant. First up is delta V. This is the holy grail. It's the total change in velocity the rocket can achieve, basically how fast and how far you can go. Next is VE, the effective exhaust velocity. That's just how fast those hot gases are physically shooting out the back of the engine. Then we've got M0, the initial mass. This is the heavy, fully loaded weight of your rocket sitting on the launch pad. And finally, MF, the final mass. This is what your spacecraft weighs after all that heavy fuel is totally burned away. The equation just ties these four things together. So what's the real-world so what here? What does this math actually tell engineers to do? Well, to get the best performance, it reveals a few absolute truths. First, if you can increase your exhaust velocity, you get way better performance. This is exactly why we use super advanced tech, like ion thrusters for deep space missions. They shoot particles out unbelievably fast. Second, carrying more propellant gives you more delta V, but we know the catch with that heavy mass. So engineers have to optimize ruthlessly. They strip away any unnecessary mass. They squeeze every single drop of efficiency out of the engine designs. And most brilliantly, they use multiple rocket stages. They literally drop empty fuel tanks as they fly, so they aren't pushing dead weight through space.
All right, we've got our physics, we've decoded our equation. Let's actually put this to work in Section 4, budgeting for deep space, destination Mars.
Let's map this out with a real scenario. Imagine we're sending a probe to Mars. It's not like in the movies where you just step on the gas and leave the engine running the whole time. It is a highly choreographed series of maneuvers. First up, you do a burn just to push into Earth orbit. You got to park the spacecraft first. Then, you wait for the exact right moment and do a massive transfer burn to actually break free of Earth's gravity. Then, during the months and months of the cruise phase, you're firing tiny thrusters to make little trajectory corrections. And finally, when you actually reach Mars, you have to fire your engines in reverse to hit the brakes so you can safely enter orbit or land. Every single one of those steps requires a very specific, calculated change in velocity.
And that is exactly what mission designers call a delta V budget. Think about it. You wouldn't go on a giant cross-country road trip without budgeting out your gas money, right? Spaceflight is the same thing, just with way less room for error. A delta V budget is the hyper-careful allocation of propellant for every single phase of that Mars trip we just talked about. Planners use the Tsiolkovsky equation to map this out to the decimal point, ensuring they have exactly enough thrust to pull off the mission, while, crucially, keeping just enough fuel in reserve just in case something weird happens. If the math on the budget doesn't balance out, the spacecraft simply doesn't leave the launch pad.
Okay, let's bring this all together. What are our big takeaways from today's explainer? First, rocket propulsion is definitely not magic. It relies entirely on Newton's third law and the conservation of momentum, shoving gas backwards so you can move forward. Second, unlike a car or an airplane, rockets are totally dynamic systems. They are constantly losing mass as they burn off that incredibly heavy fuel. Third, the Tsiolkovsky equation is the master key. It's the formula that perfectly links that changing mass, the exhaust velocity, and your ultimate delta V. And lastly, mastering this delicate math is absolutely non-negotiable if we want to design the spacecraft that will let us explore the solar system efficiently.
Which leaves us with something pretty huge to chew on. As we look ahead to the future, as we start designing massive new spacecraft to push deeper and deeper into the unknown, how will our mastery of this incredibly delicate balance between mass and momentum dictate the ultimate limits of humanity's future among the stars? It is an absolutely profound engineering challenge, and one that all starts with the simple physics of just pushing back. Thank you so much for joining me for this explainer, and hey, keep looking up.